Now talk about the linear and time invariant and convolution. The system response can be find out from the impulse response and the convolution operation. In case of linear and time invariant system, we can apply convolution operation like this way. This one is a discrete time convolution, and this one is a continuous time convolutions. First one, commutative property, it looks like this one. As we already talked about this one, xt convolution hn equals to hn convolution xn. It can be seen here that this is commutative property. Xt is applied to the system, and this becomes the output, yt. So this means that x convolution h x convolution h is yt. And here that if we exchange the system with the input, so system impulse response applied to the system xt, then yt will give h convolution xt. By exchanging system and signal, there is no difference. So this property is called commutative. We can safely exchange system and input signals. Okay. The second is associativeness. Associativeness, if xt is applied h1 and h2 like this one, we can convolution this one first and then apply this one are the same as we know that the commutative property, so we can exchange this one. We can apply this one first and this one later. This is the same property, and also we can using this one calculate first and later we apply the h2. Whatever we calculating or exchanging, it doesn't change. That is associativeness. So we can apply any pair of signal response first. It doesn't matter the sequence. We can do this one first, or we can do first this one, or we can exchange this one. It doesn't change the system response. That is associativeness. The last one is distributiveness. Input is applied both of the H1 and H2 systems. Then each one is applied like that. And because of this one is a linear time invariant, we can summing up that will be the same response. Okay, here shows that one input xt applied both of the H1 and H2 system, and the output is added up. That is output yt. This output yt are equals like this one. H1 and H2 is added like that and applied xt. That will be the same result will come out. So this property is called distributiveness. So LTI system satisfy these three conditions. The next one is a causality of the LTI system. LTI system is called causal. If the impulse response ht is 0, if t is less than 0, it means that the impulse is applied at t equals 0. You know that delta t is non-zero only t equals 0. Okay, this is non-zero only t equals 0, but the signal can be exist at after t, after the event. Then cause and effect is satisfied. That kind of system is a causal system. If it is not, it is called non-causal. Okay, here shows a non-causal system example. Event is applied at here. Okay, this is impulse. Impulse is applied at t equals 0. The response exists positive time and negative time. But this negative time area is response before the event. Event occurred at t equals 0, but the response exists before the event. That kind of behavior called that non-causal. This one is causal part, response after the event. This one is causal part, this one is non-causal part. Think about when we taking the convolution, we are shifting, reverse and shifting. Shifting means this time is t. This 0 becomes a t. And the reverse means non-causal and the causal part reversed. So this one is a past history part, past input. But this one is a future input. Future input affecting at the current time. That becomes a non-causal system. The last one definition is Beaver stability. Beaver means boundary input. If input is bounded, the output should be bounded. That kind of system is called pivot stable system. So pivot stable system means input is bounded, then output also bounded. If system satisfies that condition, we call that is pivot stable. Suppose that the input xt is bounded and all the time. Then taking the convolution. In that convolution, you know that output is taking absolute, then the absolute value of yt, absolute value of yt can be absolute value of x and h convolution value. So convolution operation are given like this one. But equality problem, you know that the sum of absolute value is always less than absolute value summations. So this one is valid. You know the equality is applied. All the internal components are positive cases, it's equal. So we can think about this convolutional output always less than this value. But we assume that the input is bounded. Okay, input is bounded. So the maximum value, the input is less than b. So we can safely write this one, and this should be bounded. So to why the output to be bounded, the absolute integration of impulse response should be bounded. This is minus infinity to infinity. It's a typo. So the absolute value of impulse response integration should be bounded. These conditions guarantee the output is bounded. So if input is bounded, then output is bounded. The condition is impulse response is absolutely integrable, then system is pivot stable. So at here you need to understand the definition of a pivot stability. Pivot stability means that the input is bounded, then output should be bounded. If the system satisfies this condition, we call that is a pivot stability. Then what requirement is what is the requirement for LTI system to be a pivot stable? That's this one. The impulse response is absolutely integrable, then the system is pivot stable. Okay.